marketplace, all these different companies, and then it's brand new on the shelf, and maybe there's a coupon for it and all this stuff, but you can't memorize everything. And you're not gonna memorize every antibiotic. However, on this exam, there's an antibiotics table. And I think there's one on the review practice as well. So there should be an antibiotics table on the the document associated with this PowerPoint. Has anyone looked at that yet? Okay. Well, yes? You have somebody looking at it now? Okay. And there is a table there? Yes. All right, then you know what to prepare for. So prep it ahead of time. Okay, you gotta prep that ahead of time, and so that you come in here and you just brain dump your antibiotics table. Okay? That is typically worth something on the order of at least 10 points, sometimes 12. So that is just, 12 points in your back pocket if you've studied it. If you haven't done it, and at the last minute you're trying to borrow your friends, it's like, this is not gonna work for you. Okay, it's like, you have to spend time on it, right? That's just how this goes, all right? So, we're working towards it in that regard. Okay, so, antibiotics, they have a long history, really, earliest, and I'm not asking about the names of these people, okay? But Paul Ehrlich, a long time ago, used arsenic, okay? Now we know that, you're not supposed to use that, okay? Because it's gonna hurt you, but it worked on syphilis, like, okay, right? So, and we're still looking for something that he coined this term, magic bullet. And it's still in use today. So I used to work for a biotech company in Berkeley, and we talked like this all the time. We just wanted the magic bullet to kill only the cancer cells and nothing else. And it doesn't quite exist yet. I'm hoping for that. All right, but this is the first antibiotic, penicillin, and we need to know every last thing about penicillin, up and down, backwards and forwards. So this is one of the slides that we should know. And so I've had people ask me, which slides do I need to know? For this antibiotics PowerPoint, I can assure you every single slide is of great importance. This is an incredibly important topic for people going into healthcare. This is one of your tools. Okay, so this is an image of a plate from, his name was Alexander Fleming, 1928, Scotland. And he was working with Staph aureus. Okay, so Staph aureus, and you see the colonies on the plate, okay, that's fine, all that's good. And he came in the next day to see the growth, and then there was this contaminant. And that's happened, and there was a mold. And we know what molds look like, kind of hairy. Okay, and that's not showing up in the image, but you see that it doesn't look like the Staph aureus at all. And then, I'm serious, if it were me, I'd probably be like, oh, that's moldy plate, just go put it in the bucket, right? But he was like, check it out, the Staph aureus can't seem to grow near this penicillium colony. I wonder what's going on. And this is what we're trying to do in lab, right? Oh, I said we were gonna take pictures of that today. All right, that's on me then, I gotta take pictures. That's fine, I'll do it. Because we're gonna have overgrowth otherwise. So he basically just started isolating the penicillium, and long story short, they isolated penicillin from it. But it's this zone of inhibition here that caught his attention. Okay, and that is what we're hoping for, that's what one of our, isolated bacteria from the soil has given us. And remember, I said if we get one in the entire class, that's a win. Okay, so yes?
For the zone of inhibition that's being shown in this image, I can't help but to see that colonies that are near the penicillin. Is that like...
So, they're not like completely inhibited, but you can see they're not big and robust like the ones that are further out, and that's what you noticed.
Just the difference.
Okay, so then I always ask this, you've got to know 4 different considerations when administering an antibiotic or prescribing an antibiotic. So I say 4, but really it's 3 of your choice, and 1 you have to know and everyone must know. It's the first one here, selectively toxic to the microbe, but doesn't harm the host. And that means it hurts them, not you. And that is always our very first criteria. With patients, you know that MDs take the Hippocratic Oath, and you've probably heard it paraphrased before, right? First, do no harm. Okay, that's gotta be your first standing criteria. And so, selectively toxic to the microbe, non-toxic to the host, and then in parentheses, I added IMF. And that means internal microflora, right? Or internal microbiota is another way to describe it. And that's just the recognition that you currently have inside of you normal bacteria in your gut. We also have it on the skin, but the skin doesn't seem to be as affected by rounds of antibiotics as the number of normal bacteria that we have in our gut. It might just be because of the, just actual surface area, right? There's just more of it. We kind of understand this now, and people who are, especially in the hospital for some time, getting like an IV of antibiotics are given yogurts to try to boost the bacteria, because we're just recognizing the antibiotics, they're just chemicals, they don't know what they're doing. They're just, if they're after bacteria, they kill them all. They're not specifically looking only for the bad guys, okay? So that's one consideration. Secondly, microbicidal rather than microbistatic. So we had this conversation before. Static means to keep it at the same level, and that would work perfectly fine if your patient has a decent immune system. All you want there is just to keep the numbers from getting bigger, okay, and let me catch up, because my immune cells are dividing. We can see white blood cell counts go up during infection. That does occur, but I told you that's 24 to 26 hours for one cellular division. I can't catch them without a little help. Okay, so just keep them at bay and I'll get them. So that works great if your patient has a decent immune system. If your patient has any kind of disorder that would inhibit their immune system, or if they're on like a low dose steroid because they have also received like a liver transplant or a kidney transplant, or any kind of organ transplant that isn't from their identical twin, then their body would currently reject that organ, and so they're put on a low dose steroid so that they don't reject. But what that does is sort of stall out your immunity. And so you don't want microbistatic for those people, because they're not going to be able to catch up, right? Bless you. And the other thing is that we'll come to this realization towards the end, and that is with a robust immune system, it requires a lot of ATP, a lot. And so that means your body can't be currently trying to fix something major. So somebody who's like just been in a really bad car wreck and has broken their femur, the biggest bone you have, they have a lot of ATP that they need to direct towards making that bone heal, and that's less available to them to run a decent immune system. So it's just, these are just like the little considerations. How's my patient? Right? Then I decide which way I'm going to go. All right, relatively soluble functions even when highly diluted in bodily fluids. And so that just means, just like we said, you can use a cap full of chemical in a gallon of water, right? And that it would still work or whatever. It's kind of the same thing here. I want to be able to give a low dose and it still works. I don't want to have to give a huge amount, because once you put it in your body, it's now reduced in effectivity. So I don't want that. Remains potent long enough to act, is not broken down or excreted prematurely. What this means is it would be great if I could give somebody 1 pill a day. That's it. Okay? The worst kinds of prescriptions, as the clinician, is something that would require like every 4 hours. Because unless, if the person is in room number 11, then yeah, the alarm goes off and you're going to go in there and you get the pill on time. Okay, fine. But for normal people, you feel bad, you get this stuff from the CVS, and you'll take it every 4 hours for the first day or 2, and then you forget. Then you left it at home, and now you're in the city. And then you get home, and then you think, what should I do? Should I take 2? Like, then you're not sure what to do. And right away, you're like falling off the course, etc. Yes?
Your date's covering this.
Oh, I'm so sorry.
That's okay, it's not your fault.
Hopefully that didn't screw too much. Okay, so doesn't lead to the development of antimicrobial resistance. This is a big deal. I sure don't want to make resistant strains. Complements or assists the activity of the host defenses, and we'll see that some do actually kind of take a toll on my immune system. Remains active. This is kind of the same thing as remains potent. Okay. Readily delivered to the site of infection. This one's tricky. This one's really tricky. Now, if you have a topical issue, okay, I can put the antibiotic right on the problem. But let's say you have an infection and it's like in your toe. And so you get a pill and you swallow it and it's like, what fraction is getting to the toe? So these are the considerations we have to think about. All right, reasonably priced, of course, that's always part of our thought process and does not disrupt the host health by causing allergies. That can be a problem, or predisposing you to another infection. So I want 4 off this list. Well, 1, you gotta know this one, plus 3 of your choosing, okay? All right. We can administer antibiotics in more than one way, okay? So IV is far and away the best way, because within moments, it's at max dosage. Okay, and that makes perfect sense. I mean, it just gets into the circulatory system so that within 1 to 2 minutes, it's now all throughout the body. Perfect. Okay. However, what just happened to my affordability? Yeah, because that means I have to go into a clinic, okay, the hospital, something. I got professional people working on this. There goes the price. Okay. So the next best is intramuscular, but I'll make you notice here, this is not up here as we see with intravenous. You have absolutely agreed to less by an intramuscular injection. And so if you lived elsewhere on this planet, you can go get one at the corner of bodega. That's not a big deal. They have signs, like, we will do that here. Okay? But that's not how it goes here. Okay, it is a rarity to get an IV of the antibiotics. That can happen if you're hospitalized or something. Getting an injection, that I've only heard of that happening a few times for people. Typically, you just can't keep anything down, and then it's like, okay, just come in here and give you a shot. Okay, otherwise no. And then the worst one is the one you're doing, oral. Okay, it has the least amount that is actually available to the body. It takes the longest time to get there. It's not great. Okay, now this is for various reasons. Part of it, and we'll see, is because most of these antibiotics, they got a little bit of side effect. Some are worse than others, but side effects like fatigue and stomach upset and this sort of thing. Yes?
What does SC stand for? After IM?
Parenteral is, so like sub-Q.
Okay.
Yeah. So, I forgot what I was saying. Okay, I don't know. Anyway. Side effects, right. So because of the side effects, we do things orally over the course of like 10 days. If you have a pet though, like a dog or something like this, and they get, an infection in their ear, and you finally figure out that they got that infection, then you take them to the vet, and they get the entire dose in one shot. Bam! So imagine that's what they did to you, the whole 10-day course in one shot now. So, and if you have had to do this to your pet, then they just go hide in the corner all day because they feel awful. Okay? But we don't do that to our patients, so it's like, okay, you're just gonna dose yourself every day for the next 10 days or whatever it is, okay? Because of this. But we just gotta recognize this is not the most efficient. Okay, cost goes into that, and it's also the side effect thing too. We can take it course through the IV, topically, as I said. Rectal, you know, this is like for babies usually. Okay, you can have a transdermal oral inhalation. I have not personally worked with anything like that, so I don't know. But
I've never heard of transdermal for antibiotics. How would that?
yeah, no, it's like a patch. It's like a slow release patch. Yeah, there's been actually a lot of research on trying to get the patches to work really well. So you've heard of people trying to quit smoking, for example, right? So they tried, once they figured that out, that you could have this low release of, I guess it's nicotine for these people, just kind of like low release, that, well, couldn't we do that with other things too, you know? And I know that they do that for like some dementia patients. There's like an acetylcholine, that's a neurotransmitter, that's a patch. They usually put it on their, like the middle of the back so they can get to it, you know. But like it's a low release, you know, like just kind of leveling off their moods and, you know, what have you. Yes?
Does the dosage of antibiotics depend on like body weight or
Oh, yes.
the type of
Yes, it's usually a body weight thing. So I mean, we've probably all been to the doctor, and it's like that's like your first thing is go weigh yourself, because it's all like milligram per kilogram and stuff like that. All right. So this leads us to this. Okay, I'm finally warmed up, and this is like every time. It's like this. It takes like 40 minutes. Okay. So this is a very important slide. So this is of this super important slide that we need to know. Slide 6 is one of those that like I would just pick out of here and add it to on my very important slides to know for microbiome. Okay? Because this is the therapeutic index. Now I want to tell you that therapeutic index exists for every single treatment that you would ever give a patient, not just antibiotics. So, and I'll describe some other medicines in a moment. So the therapeutic index, first off, is a 50% value of the population that's tested. And the tested population, I think I've told you this before, because I went to an institution like this as an undergrad that had a medical school. Okay? And medical schools will put up posters where the undergrads walk by, like, hey, join this study. Okay, for $200, $500, whatever it is. The more, as you know, they're really going to hurt you on these things. You know, I never take part in anyone, but that's who they're testing. And so the problem with these numbers is that you're talking typically, and they open it up to the public, but typically they get a ton of undergrads. And so what happens is you're looking at a population that's between 18 and let's say 24 years old. Those are the healthiest people there are. So when we get these values, you're always like, because my patient is 78 and on a respirator or whatever, like we got to take these numbers with a grain of salt. Okay? So what we see here in the therapeutic index is a ratio between the toxic dose and the effective dose. So what does this mean? The blue line is the therapeutic dosage required to see a reduction in the symptoms in half the tested population. Okay, so I'll see a reduction in the symptoms at this value. So if I give less than that, there's some people that will in fact respond. But if I give that value for some people, that's not doing it. You have to crank it up. Okay, that's the problem with an average. It's not, it might be all right, right? But it's just a kind of a gauge, all right? That's how much you would have to administer to see an effect. So that's the effective dose for half the tested population. And the toxic effect is the dosage where you start seeing the side effects, right? That's where you start seeing the side effects. And what we want for therapeutic index, and that's the ratio, and every drug and every treatment has it, you want to see that these two curves are far away from each other, right? If that's the case, that the toxic dose is far away, then what that means, if I were to do dot, dot, dot and go straight up, do you see that this would be here? Like the max dose, which you don't need to do, like you don't need that, right? So what that means is, if I stick to a dose that's way over here, it's very unlikely, in fact, according to this curve, it's 0, that I would get any side effects whatsoever. That's what I want, because that's my #1 criteria, hurt them, not me, okay? The problem is that we have a lot of drugs where this is the effective dose, but you see that the toxic dose is right here, okay? And so with these two, they're too close together. And because that's just the 50% mark, for some people you have to use more, okay? And now you're in the toxic range. Now you're in the range where they are in fact going to get side effects. So the worst drugs, antibiotics that we know, okay, are gentamicin, amphotericin B. This is actually an antifungal. All eukaryotic organisms are going to pose a problem for me because their internal structures are a lot like mine. Okay, so it's going to be hard to target them, not me. And chloramphenicol. So these are rarely used in the United States. They exist on other parts of the globe because they're inexpensive, but they're toxic. So, all right, and I have, even though this is so the actual terms are that this would be a narrow therapeutic index, and this is a broad therapeutic index, but because we already are using the terms broad and narrow about spectrum, whether it hurts gram-positives and negatives both, that's broad, or only one or the other, that's narrow, I want to stay away from broad and narrow at therapeutic index and call them bad and good. Okay? So broad, good, narrow, bad, and that's how we're going to talk about it. And I know that I'm kind of dumbing it down a little bit for you, but I don't want in the high stakes atmosphere of an exam that you get them mixed up. Okay, so we're just going to stick to bad and good, but you, in your back of your mind, you've got to remember, because that's not how the books are going to talk about it, and that's not what you're going to see on any kind of chart. They're going to use broad and narrow. Okay, so we can still see that even though this is narrow, that there is in fact a gap. Here's some drugs that are far worse. Okay, here they are. So some drugs that are far worse are like almost all chemotherapies. So like chemotherapies, oncology drugs that they give people with cancer, they literally, you can look it up, they're right on top of each other. Meaning that there is no dose at which you could administer this that doesn't have side effects. Nothing. Even the least amount will cause an effect. And of course, greater amounts will cause more. So every single drug has a therapeutic index. Okay, what you want is a big number, okay, not a small one. Okay? So the big number would be if the toxic dose is, oh my gosh, you have to give so much, right? Based on how little you have to give for the effective dose. Okay?
What is the ED and the TD? The D
Effective dose for half the population.
Okay.
Toxic dose for half the population.
Okay.
Okay? All right, so though the first antibiotic discovered was penicillin and it's from fungi, the majority of antibiotics are coming to us from soil bacteria. And they're almost all gram-positive soil bacteria. Okay? If you think about soil, because you've looked at it, there's a ton of stuff in there. Antibiotics are a mechanism, a way that some bacteria can kind of get an edge on their competitors. Okay? So we have lots and lots of different antibiotics. Some of these on this list that you'll recognize, bacitracin and polymyxin, both of these are in the triple antibiotic ointment that we can just buy over the counter. Both of the, and we, Bacillus subtilis, we work with that, right? So, like this is a known thing, and then look at all these streptomyces. That's what we've been trying to pull out of the ground right now. So a lot of them like that. And there are some from fungi, but the majority are from gram-positive soil bacteria. And so this is an important slide because this is what they do. Okay? So again, if we haven't established in our own mind what it is to be a prokaryotic cell, a bacterial cell, and all the pieces and parts of that, then this is a confusing slide. If all that's like, no big deal, I know that stuff cold, then this is easy. Okay, so just looking at all of this, we can see that there's 5 different classes. So in the table, that's the first column, are the classes. So first off, inhibition of cell wall synthesis. Okay, cell wall, and we know that all asterisk bacteria have cell walls. Who does not? Well, bacteria. Mycoplasma, but that is a good point, Amelia, that you're not going to be able to take a cell wall synthesis inhibitor for a viral infection because they don't have a wall. In fact, none of these will work on virus. But mycoplasma, as Mary Bond just said, lack a cell wall. And that's something that we know from Unit 1. Okay, so that comes with us. Because if your patient has a UTI or walking pneumonia and it's mycoplasma, you can't give anything from this category. It's useless. They're not planning on making a wall. That was not their plan. Okay, that will not hit them. Okay? But knowing what you know about gram-positives and gram-negatives, who has more wall? Okay, so these are going to work preferentially on gram-positives. So will that be broad spectrum or narrow spectrum? That's right, narrow spectrum. It'll be mostly for gram-positives. But then, if we have this other thought about therapeutic index, which means hurts them, not me, then we have to consider this. Is it my plan to build a wall? Do I have a cell wall?
No.
I'm gonna look over here until we get it. We don't. Human cells have a plasma membrane only. So a cell wall for that is peptidoglycan, right? NAM-NAG, cross-linked with amino acids, yes? And they're not just amino acids, they're D amino acids, like really weird. So go ahead and hit that, right? It's not the wall that will be attacked, it's the enzyme responsible for the cross-linking, and we'll get to that in just a second. But if that's the case, I don't possess this structure, then that makes a great target. Okay, therapeutic index, because that's my number 1 criteria, right? That's it. Don't hurt me. Don't hurt the patient. Does that make sense? That's our overriding theme throughout this lecture, okay? So, without even going any further, all we have to think is, do I possess the structure or the process? If the answer is no, that's great. That's a good therapeutic index. If I possess the structure or the process, does this little chemical know that that's not the one I want to target? Or does, a chemical has no idea, right? They're not sentient creatures, they're just after stuff. Okay? So, cell wall, we don't have that. Okay, now, protein synthesis. Is that something I do? Yeah. Yeah, it is. Okay, so that's going to have more likely side effects. Folic acid synthesis. Okay? And the thing is with this, you really want to think that that's something that we have, but we don't. Here's the deal. You have to have folic acid. You need it because it's the precursor to nucleotides, ACEs, GCs, and U. Okay? It's absolutely necessary, especially for pregnant women because they're doing a lot of cellular division, right? And so they need lots of ACEs, GCs, and U. Okay? But human beings don't know how to make folic acid. You have to eat it. Dark leafy greens and a pill. That's the only 2 things I know. I'm not a nutritionist, I've said this before. So if some of you have like some special thing that you can eat, please let the rest of us know. Because all I know is the dark leafy greens and the supplement. I'm not sure. But I don't know how to do this. So this is a great target. Okay? Don't let that get you confused. The fact that you need folic acid also, but you don't know how to make it. That's why you need it. You don't know how to make it for yourself. Number 4, inhibition of nucleic acids. Okay, nucleic acid replication or transcription. Do I copy my DNA?
Yeah.
Yeah, do I make message?
Yes.
Yeah, okay, so tell me about the therapeutic index. Good or bad? Yeah, not great. Not great. And then injury to the plasma membrane. Do I have one of those?
Yes.
Yeah, I do. So that's not great either. So I got 2 out of 5 that have a good therapeutic index. 3 out of 5 have a narrow therapeutic index. And here's the bad news. Do we knowingly give medications of any kind to our patients knowing that there's side effects? Yes, we do. All of oncology, right? Okay, here's what's gonna happen to you. You're gonna lose your hair. You're gonna feel like nothing, right? Right there. And so am I gonna administer drugs that hurt my patient? Yes, yes, that's gonna happen. I don't want to. I want to use the other ones if I can, okay? But what we think is like if it's just like a 10-day course, you can live with that, okay? Something. Does that make sense? All right. So this is an overriding slide here, and we'll start with number 1, inhibition of cell wall synthesis. And so we recall that both gram-positives and negatives have a cell wall, a peptidoglycan cell wall. It's much thicker in the gram-positive. And what the cell wall does is it provides stability in hypotonic solution. It keeps the cell from swelling and bursting. Now, you know, it's running pumps too, but the wall really helps with that. The wall is no good to any given cell in hypertonic solution. We know that that drags water out, right? Okay. And so this is an actual electron micrograph image, scanning electron micrograph image of bacteria. These are obviously bacilli before and after penicillin, and you can see the big gaping holes there. Okay. So that what happens is that it's going to inhibit the synthesis of the wall. It doesn't inhibit the wall itself. What it does is it inhibits the formation of the amino acid cross-links. So we know that that's what peptidoglycan, like even if you're just thinking about the word and breaking it down into its 2 halves, the glycan are the alternating sugars that make the glycan rods. And then the peptido part is because there's amino acids that are part of the cross-link, right? They cross-link one glycan rod to another. And so remember I said that like if you're talking about making a raft, okay, the glycan rods would be like the logs, and you have to tie them together for this to have, you know, any structural integrity. What we're not thinking about though, because we're looking at it in just one plane, remember if you're gram-positive, you have 20 layers of this. So you actually have other linkages with amino acids going up, okay, for the layer above, and that would happen again, right? So you've got tons of amino acid cross-links, okay? And so penicillin is going to stop the cross-links from occurring, and I'll explain how. So transpeptidase is an enzyme that does the cross-link. So unfortunately it's drawn really small. This would be kind of big. If these are only 2 amino acids, transpeptidase is an entire protein. It would be bigger than this, and it's what does the cross-linking. So it takes one N-acetylglucosamine and N-acetylmuronic acid, and it's always the muronic acids that are cross-linked. It hooks their amino acid groups together so that now they're one long group. Okay? So it's an enzyme that does it, transpeptidase, very important enzyme. And so this is how almost all antibiotics work, is that they are competitive inhibitors. Are you familiar with that term? Yes and no. Okay. So what it means is this. Transpeptidase, do you know what ACE means at the end of the enzyme? Okay. So all enzymes have an active site. So that's this little cleft here. Okay. And that active site is where it's doing the reaction. Okay? And it binds to the substrate in the active site. A competitive inhibitor jams up the active site. It gets in there and it's stuck. Maybe you've heard of enzymes and substrates described as locks and keys, okay? So imagine, and maybe you've even had this experience, that you put a key into a lock, but that's the wrong key, and now, but it's enough like the real key that I keep getting out, it's stuck. That's what happens. That's how penicillin works, and a lot of other antibiotics work exactly like this. They stop enzyme activity. So I want us to be careful here because I'm inhibiting with penicillin this enzyme, transpeptidase. And it's pretty easy to remember what it is that it does if you remember what peptide means, okay, the cross link between amino acids, and trans just means, across. Okay, so that's what this is doing. And so penicillin like jams it. And the reason it jams it is because penicillin looks just like or very similar to the real substrate. Remember I said that the amino acid cross-links are with D amino acids? Okay, so, and we're not going into enantiomers right now. That was, that's your chem stuff, Chem 60, Chem 1A, they established that for you. But these are weird to me. Humans don't use the D format. So this is the substrate, and this is penicillin. And I'm not asking you to, I will never ask you to draw a structure in this class, okay? Just look at it, that's all I'm asking. And if you're looking at it, they look a lot alike. Okay, I see, carbonyl, nitrogen, another, look at this, it looks exactly the same, right? Some methyls, okay, we got a couple methyls. It looks enough alike. Transpeptidase is an enzyme, I love proteins, it doesn't know what's happening. It just has a mouth that looks like this, and if penicillin sits in there first instead of the D-alanine, then it can't do its job. No cross-linking means that these rods are now just loose and slipping past one another, and you get a big hole, like I showed you in that other image. Okay? So, penicillin is a competitive inhibitor because it looks like the substrate. This part we do need to know. Right here, see this box? Okay? This is known as the beta-lactam ring. Let me draw something here. Okay, I can draw. Great stuff. This is not that. Okay. This is the beta-lactam ring. So I'll just write out the word beta, but I like it when I can use the Greek one. So beta-lactam ring. Okay, that's the real chemical name, but I call it the box. Okay, and the reason I call it the box is because, while yes, in chemistry this is a ring and this is a ring, if I say the beta-lactam ring, you might not, I don't remember which one is it. Is it this one or this one? But if I say the box, there's only one box showing. Okay, there's one box. This is a little house. Right? Okay, so this is the beta-lactam ring. Okay, we call it the box. All antibiotics that have this structure are the beta-lactams. And we'll see that that's penicillin, ampicillin, amoxicillin, oxacillin, methicillin. There's a lot in this category. They all share this same box. And they all work the same way. They jam up transpeptidase. Okay? So this is our competitive inhibitor. And so it stops, penicillin gets in the mouth of transpeptidase, that's what I tried to show here, and now you don't get the cross-linking. So remember this last image here, you get a nice cross-link at the end, not if penicillin's there. Okay, you can't get it. Thing is though, gram-negatives are more resistant to penicillin. Okay? And the reason is because of the porin and the LPS, they repel anything large and hydrophobic. And penicillin's not particularly big, but do you see these boxes? Okay, carbon to carbon bonds, what do we know about that? Polar or nonpolar? They're nonpolar. Okay, so that means it's hydrophobic. Okay, so your box, your bunch of rings, you're hydrophobic. Okay, I got the porin and the LPS, like no, no, and no, can't get in here. And even if some manages to get across, what's meeting it on the other side of this outer membrane? what's in here? What is this fluid layer?
No.
The periplasm, and what's in that periplasm? Hydrolytic enzymes, chop, 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 chop. I already told you that to be a gram-negative meant that you had, anything trying to get in has to run the gauntlet. Get past the outer membrane, if you can. Then get past my periplasm, if you can. Right? So they have this built-in mechanism. And so because of that, gram-negatives are more resistant. And if that's the case, we're looking at a narrow spectrum. Okay, the problem with saying narrow spectrum is it's not built in like, well, in which direction? Right? I just know when it works on one, not the other. It doesn't let me know that I'm talking about it only works on gram-positives. Okay? All right. We have another little problem with penicillin. Oh yes, Simone.
Sorry, this isn't related to this. I just want to make sure I wrote down the right thing. Of the narrow and broad curves, which one's bad, which one's good?
Well, the bad and good and therapeutic index are not the same thing. Okay, so whether it's broad spectrum or narrow spectrum is unrelated to the therapeutic index. These are different thoughts. Okay, that's why I'm trying to, does that make sense? Some bacteria are resistant to penicillin because they have an enzyme that cuts the bottom of the box. Okay, that is known as either penicillinase or beta-lactamase because this is the beta-lactam ring. Okay, so they cut the bottom of the box and this is what you wind up with. Okay, and so they have an enzyme that cuts the box. Now, penicillin is not tricky. It will not sit in the active site of transpeptidase. It's now rendered useless. And I recognize that to us, looking at this two-dimensionally, it's like, big deal. So just draw the line, who cares? But if we built this with balls and sticks, we would now be missing a link, right? So instead of being a rigid box, instead you have single bonds here all the way around. That's ultimate rotation. This thing isn't rigid and sitting in that little cleft, which is the active site of transpeptidase. This is not tricky at all anymore. That doesn't look the same. Okay? So if you took that same key that went into the lock and it wasn't supposed to, and you clipped off one of the little points, for example, that's not tricky now. That lock is not full now. Okay? That's what we're doing with this. So some bacteria have that. The penicillinase or beta-lactamase. Either is correct. So I was talking with my colleague about this, Katie Jamshidi, who's currently the chair, and I was saying, you know, my students always get mixed up on the exam, transpeptidase and penicillinase. Okay? You have to just get used to these names, but better, draw yourself a picture or look at these slides. And then you're not going to get them mixed up. They just have names you're not used to. That's all. Okay? All right? So the names aren't, I mean, they don't really sound alike. They just have an ace at the end. I mean, I don't, to me, it's like, it's like confusing, you know, the name Jim and, you know, Antonio. Like, what? No. I'm not going to confuse it. But to somebody who hasn't heard any of these names, it all sounds the same. I get it. But you gotta just kind of look at it, because I will ask it. Remember, I said we will know everything about penicillin, top to bottom. How it was discovered, what it does, sits in the mouth of transpeptidase, acts as a competitive inhibitor. Okay, what the beta-lactam ring is, I should be able to recognize it on any picture of penicillin, and then know that if I clip the bottom of the box with beta-lactamase, aka penicillinase, I'm gonna get something that isn't tricky at all. Yes?
Is there any truth to penicillin also coming from moldy rye bread?
It might. I mean, if it has the penicillium organism there, that's actually one that I know very well, that fungi. So if we had some mold, and I took even a wet mount and looked at it, I would recognize it right off if it were true. But not all molds are making antibiotics, so I wouldn't necessarily, and you know, some molds are really bad, like what happened to the poor Salem witches, right? So, like, we're not just taking weird molds.
Yeah.
We're not doing.
What happened to sandwiches?
Right, so here we have this. All right, and so natural penicillin, so the one that actually comes from the fungi, has an incredible advantage in that it has a good therapeutic index. And remember what that means? Hurts them, not you. And why is that? Is because humans don't have transpeptidase, we don't cross-link with amino acids, and I don't have glycan rods. I am not making a wall. So go ahead and target it. The problem is there's a couple disadvantages. First off, it's narrow spectrum. So you have to know for a fact that your patient has a gram-positive infection, which means that, you know, you did the aseptic sampling of the stool, sputum, blood, whatever it is, and you ran that gram stain within 24 hours, right? Because otherwise, we have this little issue, and I can't go into it because it's not fair, okay? We have an exam in a moment. So that's fine as long as I know I have a gram-positive I'm dealing with. Otherwise, that is not what I want to go with. It is susceptible to getting cut at the bottom of the box. Okay, that is an issue. And for some people, they can have allergies. Now, it doesn't always go hand in hand, but sometimes people with mold or fungi allergies sometimes have an allergic response to penicillin. However, let me tell you that there has been a big study, it just came out recently, that of all the people who say they're allergic to penicillin, fully 90% aren't. So people think they're allergic because they're getting the side effect that their stomach doesn't feel 100% while they're on it, or something like this. A true allergy is the rash or the anaphylactic. So we really, really keep hammering. Notice all the disadvantages. Why do we keep using this kind of thing? Is because of this right here. This is my #1 criteria. So this is why. So if this is the case, here's some things I don't like about it. This is where the chemists come in like, okay, let's see if we can fix this. So there's a couple semi-synthetic penicillins like oxacillin. Okay, oxacillin is actually bigger than normal penicillin. So is this going to get into a gram-negative if it's even bigger and even an extra ring?
Absolutely.
No. But what does happen is that in solution, these two rings sort of bend over because we have a single bond here. It flips over and protects the box. By protecting the box, it can't get cut at the bottom. So any that have resistance to normal penicillin maybe don't have resistance to oxacillin. Okay? But if you have something that, you know, you have a drug that you now have trimmed down like ampicillin, so it's smaller than penicillin, now this can kind of squeeze its way past the point. So this one has now what they call extended spectrum. But is it just as good 50-50 on gram-positives and negatives? No, it's still much better on the gram-positives. Okay, but we have now extended the spectrum, kind of bumped it into some gram-negatives will in fact take this in. Now, having said all that, and the porin and all the things that it can do to keep out penicillin or even ampicillin or whatever, you know, you can ask yourself, well, what if I kept upping the dosage? Would a fraction get through? Absolutely. Well, why don't I want to just like, if one, you know, pill is great, why not take 10? Why don't we do that?
Your side effects go up.
Side effects, exactly. That is exactly it. So with drugs, it's the opposite. It's not like cookies. Okay, so if you want to give the least amount possible, that's why they do all these studies on people. Like, well, what is the least amount I can get away with to get an effect? I don't want to give the max. I want to give the least. Okay. All right. So that. And so this is just for you have a table, and you're going to choose one antibiotic per mechanism, and there's 5 mechanisms. The thing is, penicillin's off the table because everybody's got to know that one. So just pick something else. Amoxicillin, ampicillin, you know, whatever. I'm going to skip this cephalosporin and carbapenems unless you've been on one. But we'll go here to amoxicillin, which is very often given. Okay? Amoxicillin on its own sometimes doesn't really work that well. See, this is like the number of so the black line, the number of bacteria growing, right? And you know, we would hopefully at some point flatten out, but okay, here they are growing exponentially. If you give amoxicillin alone, sometimes nothing happens. Like it's not really, okay, it's less, but I'm not happy with this response, right? If they pair it up with clavulanic acid, what it does is that it sits in the mouth of penicillin ACE, which is itself an enzyme. Okay, it's looking for penicillin to cut the bottom of the box. If you give it clavulanic acid, penicillin ACE can't work. So if you mix together amoxicillin and clavulanic acid, that's called augmentin, notice that it kills. It works great. Okay? So there's a lot of beta-lactam antibiotics. They all share that same box, like penicillin, and there's many, many different ones. You might know of one that I haven't named, and that's okay. All right? The reason why there's so many of them is because of that single fact, which is it has a good therapeutic index. And when that's the case, and that's my number one criteria, then I keep hammering on that door. Which one is the one that will work best? Because the likelihood of hurting the patient is very, very low. Okay, the patient does not have transpeptidase. Okay, the patient is not going to do D-amino acid crosslinks. Not happening. Okay? All right. So we do have side effects. And so, you know, I think the table has a advantage, disadvantage column. Okay? Is anybody looking at that right now? No? Okay. It's in the documents. Okay, so there's an advantage, disadvantage column. And so, you know, and students will say, I can't find any advantages. It's like, does it have a good therapeutic index? That trumps every other criteria, even affordability. Okay, number one, doesn't hurt them, that's the one. Okay, side effects, lots and lots of different things. Okay, allergic reactions, of course. For some people, liver function issues. Okay, encephalopathy. Okay, so the swelling of the brain, that might happen if like high dose, but like it really shouldn't have to go there is the thing. All right, so all right. There is another way around though, because we have entire classes of bacteria that do not respond at all to any beta-lactam. Not penicillin, not ampicillin, not amoxicillin, nothing. None of those seem to work. So they go end run. Okay, fine. I can't stop the transpeptidase. Let's see if we can use these drugs to mop up or bind to all the D-ALA substrates. That's what they do. And by taking away all of the substrates, there's nothing to use to cross-link. So even though the enzyme would work, there's nothing to use. Okay? These two drugs are vancomycin, right here, and this is bacitracin. And as I said, we don't need to know any chemistry at all, but I can look at this and so I can just go like, wow, that's really big. So is this getting through the porin? Absolutely not. This is extremely narrow spectrum. Like you have to know for a fact that you are dealing with a gram-positive infection because otherwise, no chance at all. And the same is true of bacitracin. Vancomycin has some other detractions. IV only. So what just happened to my affordability? Okay, forget that. All right, high toxicity. So definitely has bad side effects, definitely not great on the therapeutic index. Excreted unchanged into the environment. What does that mean? Well, so because it's so complex, my liver enzymes don't know what to do with that thing. Like, oh my gosh, and it just goes out, okay, in our urine and in our feces, which means that it's now in the soil, which means that all these bacteria in the soil are now being dosed with vanco, okay? And only the strong of them will survive. And so unbeknownst to us, we're creating vancomycin-resistant bacteria in the soil. But, gee, I wasn't planning on that, right? This is an issue. Bacitracin is in the triple antibiotic ointment. It works well on gram-positives. We can never pack it into a wound. Like if you had a puncture and you're out camping and there's a puncture, you don't want to like squeeze the tube of triple antibiotic in there and put a Band-Aid on. Do not do that. High nephrotoxicity. Where are the nephrons? In the kidney. I don't want kidney disorders on the other end of this antibiotic usage, okay? Because I need those. And they're so highly specialized cells, it's not epithelia in the normal, they get scraped from the end, makes some more greater big deal. These are highly specialized, so I don't want to mess with this. Topical, no problem. Internal, no. Can't do it. And of course, narrow spectrum because of the size. So there you go. So Vanco also stops the cross-linking, not by jamming itself into the mouth of the enzyme, but rather binding to all of the substrate. Okay, so then this will be, I don't know if I can get it. Well, I'll just start. I'll start. We're having a little arms race with bacteria because we are forcing we're forcing bacteria to live under too many antibiotics. And by doing so, we will kill off all the ones that are sensitive, but we'll leave all the most resistant behind. Okay? So when we do that, then we have to come up with a new antibiotic, and so we're co-evolving with them. Okay, so that's coevolution is changes in one population force reciprocal changes in the other. So we're using the antibiotics as selective forces. The more we use antibiotics, the faster they become resistant. And this is our last slide for today. So penicillin discovered, for example, this is what happened with the penicillin story. It inhibits transpeptidase, but immediately they started using it way too much. And so now we killed off, bless you, we killed off all the bacteria that had sensitivity and left behind the ones that had some level of resistance, and a lot of them had the penicillinase enzyme to cut the bottom of the box. So then they created methicillin, and that is an antibiotic that's like penicillin but is resistant to penicillinase. And then they created a completely new kind of transpeptidase. They made little mutations in their transpeptidase, so now no beta-lactams work. And those are the methicillin-resistant Staph aureus. Now we just say multiply resistant Staph aureus, MRSA. We do have a MRSA lab. I'll send you out in the world with 2 swabs. You come back, let's see if we can find some MRSA. Okay. I know it sounds like you're gonna get it, but it's unfortunate. We have the same ratio of success as we do with the soil, like 2 people. But anyway, all right, we'll start here next time. This is slide 2.